Hello everyone. Looks like there has been a change of meeting link. So let's wait for them. We will start in a couple of minutes. So, hello everyone. I hope you all are doing good there. I am Arif Giri and today I'll be discussing about binary search. And my counterpart, Aditya Jain, he'll continue with 2 pointers later on in the session. So for now, due to internet issues in my area, I will be turning off my video. I'll be sharing my screen in a while and we'll get started. All right. I hope I'm audible to all and my screen is visible. I'll just check. Say yes in the chat if it's visible. Or Jen,
Yes, sir.
could you please?
Yeah, it's fine.
Okay. Here we go. Binary search. It's a very frequent topic, a common topic. It's a very useful tool in the field of competitive programming. So first of all, let us begin with what is a search. As the word suggests, search is basically finding something. In programming terms, we are searching for an element in a collection of them. And the collections we typically deal with are arrays, vectors, sets, and so on. Okay. So then, um, so this is a search. Now, let me take a basic example, that of a fruit search. It was right now, I think, mango season, but let me go with orange. Let us search for orange in this. These are all 5 fruits which are hidden to me. Let me search one by one. All right, let's start. Okay, we did not get an orange on the first try. Let us continue further. Neither on the second try, and the third one got leaked for some reason. All right, it's not in the third box as well. Oh, so it's in the fourth box. We have finally found our orange. So in this search, we basically went from left to right, going over every index of the collection of the array, if I say. So it's like first step means I went over the first element of the array and so on. So I got my orange on the fourth step. So this kind of search is called a linear search. All right. Let's proceed further. Let us search in this given array of numbers. Note that I've used a sorted array here. I'm going to explain its significance in a couple of minutes. Now, in this array of 7 elements, we have to find 15. If we use the usual way, then we would just start from 1, go over every index of the array, and then if we see first, second, third, fourth, and finally on the 5th index, we will find 15. So in 5 steps, we find the required value 15. Now think about this. I give you 1,000 elements and I keep something in the 991st element. All right. So if you do a linear search, you're going to go over 991 elements. So now, what you say? If you try to go from the beginning, it will take a lot of time because you're going over a lot of iterations. But if I go from the reverse way, I will just get it in the 10th attempt. So you may say that, okay, let's start from beginning as well as the end. Now I'll give you another situation. I'll give it 10,000 elements and I'll place something on index number 5,000. So then both forward as well as reverse will become impractical. So then what I will do is I'm going to start from the middle. All right. Let's say I have
Arav has some issue with his network connection. He will join us in 2 or 3 minutes.
Am I audible?
Yes, Arav, you are audible.
Okay, so what was the last thing I was covering? I think I got disconnected.
You just started binary search.
Just a minute. Hello, is my screen visible now?
Yeah, it's visible.
Yeah, I'm really sorry for the internet issues. Let's wait. Let's waste no further time. So did we go through the fruit search?
Yeah, you finished fruit search.
Right. And did I cover this point? Um, I just stop me where I.
Yeah, start from here.
Okay. So in essence, what we did was a linear search. All right. What I was saying was that we will start with a new kind of search. Let's find it in a new way. If you start from the beginning or the end, so then what will happen is that if you do a linear search, it may take a lot of time. So now what I'm saying is I will choose the middle element, and then what array I have, I'm going to break it into two pieces, and I'm going to select which one has my element. How do we check that? That depends on the situation. Okay, let's go. So this is that example which we were doing, which we remember did in 5 steps. So now to get the middle element, I need to know the starting as well as the ending index. All right. So I'll be maintaining some labels for the starting as well as the ending index. Okay, let's start. So initially, my starting index is pointing at this element at 1, and my ending index is at 24, and my middle is right now at 11. All right. Now, What I need to do is that, is this middle element, is it what I want? Is it 15? I'm searching for 15. No. So now you see, this is the significance of the array being sorted. Since it's sorted, I know every element left side of 11 is less than 11 and everything right side of 11 is greater than 11. All right. And now you know that 15, the element we want, is greater than 11 and it'll be greater than every element left side of 11. So there is no point of searching for 15 anywhere to the left side of 11. So I'm going to discard the left half. All right, let's discard. And notice when we're discarding the left half, our starting index will change. From 1, it will go to pointing towards 15. So from 0 index, it will go to index number 4. All right. So I discarded the left index. Now my middle index is now pointing to 17. At middle index, I have 17. And 17 we know is greater than 15. So whatever is, if this array was larger, we would discard everything right side of 17. All right. So now I'm going to discard the right half. The reason I have already stated. So please follow on. And once we discard the right half, we are going to shift the end pointer also. That is, it will be just one less than the middle index. All right. Now we are finally left with only one element, and that element is 15. So we can report that, okay, we have found 15 in the array, or you can report its index. And that index value is stored in mid. Okay, in mid or middle. All right. So let's see. I hope you guys followed on. Now you see, we used in total 3 steps, and initially we had used 5 steps. So clearly, this is the fastest search. Now you may say, Arav, that this is insignificant. It is just 2 steps less. No, actually, when you compute the time complexity of such a search, I'm not sure, but I guess you would have done it before. If not, I'll just tell you one thing. The complexity of such a search is logarithmic. And what is this search we did? Since we split the array into 2 pieces all the time, this is called a binary search. All right. So we basically split everything till we get the part which contains an element. And notice at the end, we always get one element. From say 5, then we reduce it to 3 and so on. The size of the part we want. All right. Let us intuitively build the code for this. So what is the first thing I said? If you have an array, you're supposed to maintain the position of start and end. And middle is given by start plus end divided by 2. All right. You can take a look at this itself. So here I have some 7 elements. So they'll be labeled from 0 to 6. And the middle is at 3. And you can see that it is 0 plus 6 divided by 2. So in general, this is what we will do to find the middle index. All right. It will be start plus end by 2. If there are an even number of elements, then you will say that, okay, there are 2 middle terms, but I will take only the left side one. All right. And the formula that I'm telling will take care of this. You need not worry much about them. All right. And after that, you have to first of all initialize what is start and what is end. Middle element I told you right now. Then once you get the middle element, you need to check, is that middle element equaling 15? Let me call that key. Is my middle element equals the key? If not, is it greater than the key or is it less than the key? Suppose my middle element is greater than the key. All right. Suppose I was searching for 7. So in that case, what I will say, everything greater than 7 is not of my interest. And everything greater than 7 is greater than 11 also. I mean, everything greater than the middle element is greater than 7, which is why we are going to discard the right half. And by discarding, I mean, I will change the value of the end index. All right. As we saw, we are shifting the end index to middle minus 1. Remember this. When we discard the left side, we are going to make start equals mid plus 1. All right. And whenever we have end, whenever we are going to discard right side, we are going to make it end equals middle minus 1. All right. So I just formalize this. I've written this down here. And then if it is equals, I told you, we will stop over there. So here you go. Here is the code. There's just one more point which I didn't speak of, which is that once you do this, this is one round of steps. All right. I initialize start, end, I maintain mid equals start plus end by 2. Then I'm comparing everything inside. I'm comparing this. If it equals the key, if it is less, then I will shift start. And if it is greater, I will shift the end. Now, why is this while loop important? How many iterations are we supposed to do? It is best to use a while loop here. We always use a while loop here. And we say while end is greater than equals the start. Notice, let me just go back to that. Over here, since 15 is in our array, what happens is that we start and end will converge here. And then that condition array, ARR of mid equals key. In this case, key is 15. And ARR of mid equals the key. So we are saying that it is present in the array. Suppose I don't put while and greater than equals start. Then how will it ever terminate if the element is not even present in the array? So suppose 16 was there. Suppose 16 was there. It is less than 17. We will discard right half. We'll come to 15. Then what we said, 16 is greater than 15. So I'm supposed to actually shift start by 1 to the right side. All right. I'll just show the condition. Yeah. ARR of mid is 15 in that example. And key equals 16. So I will say start equals mid plus 1. But if you saw over there, start equals end over there. It is all pointing to the same thing. So in that case, start will become greater than end. But this is not what we want. We want it to terminate over there, which is why we put end greater than equals start. And finally, at the end, I just added this line for this example. This example actually checks whether this element is there or not. All right. We are searching whether an element is there or not. So if it was 16, it would say, okay, ARR of mid not equals key. So not found in the array. Or else it would print the index as shown in that if condition. All right. I hope this much is clear. All right. Attendance time. I'm giving you a minute or two to fill the attendance. Meanwhile, you can put doubts and all. We'll resume in a minute. Okay, last 1 minute. Please fill the attendance and we will move on. I hope everyone is done by now. This will be anyway sent one more time. All right, let's proceed further. Let's take up this example closest to the left. All right. So now you're given an array of n numbers sorted in non-decreasing order. That means either they'll increase or some elements will be equal. And you have been given k queries. For each query, we need to print the maximum index of an array element not greater than the given one. Now in this, we just now learned binary search, right? So in that, what we were doing is we are checking whether an element is equal or not. Okay. But now in this, what we need to show is that what we need to find is that we can find even the less we can find even an element which is lesser than that. Okay. They just don't want it to be greater than it. So suppose in the example which I had given, 135, that one. Yeah, in this example, suppose you take this only, I can even ask, tell me an element, tell me the maximum index of the element that is not greater than 16. You can clearly see that 16 should have been here, but element not greater than that is 15. All right. So that's the thing. So now we have to suitably modify the code. All right. I will just briefly explain this because I'll be taking up another way of doing the same problem and I will use that method actually. All right. So now actually, if it is lesser, what I will do is that I will again shift start by I'll shift start and I'll say start equals mid plus 1. But remember, mid, okay, mid is actually satisfying our condition. It is one of our, what you say, prospective answers. And when we do start equals mid plus 1, we should not forget that mid itself was a, correct answer. So later on, let me take this. So suppose this is there. 11 is actually satisfying our answer, but we will still shift over here because we are trying to look for better perspectives, better answers. Maybe 15 is possible, maybe 17 is possible. So that's why we will continue with the search. All right. So that's why we should not, neglect that as a possibility. I'll tell you the reason. Now, suppose it is greater. If it is greater, then my end will shift by 1. All right. If it is greater, end will shift by 1. Okay, let me just illustrate this. All right. I will take up another example. I will let some elements repeat also. So what I'm saying, suppose I have to find an element that is not greater than maximum index of an element which is not greater than 8. All right. You can clearly see this. It is 0, 1, 2, 3, 4. All right. So now the small twist over here is that now let's find out the middle element. See, in this there are even number of elements. So this will be my middle element. All right. I told that before. So now, is 7 less than 8? Is 7 less than 8? Yes. All right. So now, initially start. Now my start was at 1. Now my start will point to 7. All right. And I will discard whatever is left side. Sorry. Yeah. I'll discard whatever is left side, including 7. All right. Whenever I'm discarding left side or right side, I'm even discarding the middle element. Okay. So this is actually my new start. And this is my new end. And my new middle element is 9. So now, when we run that loop, we will see is 9 less than 8? No. Yeah, this 9 will be given by ARR of mid, by the way. Is 9 less than 8? No. It is, what is it? It is greater than 8. So that means I will shift end to mid minus 1. That means I will shift it to 7. I'm discarding the right half. All right. So finally this, this. I'm left with this. Now both start and end are pointing to this, and even the middle will point to this. And you can see that the middle element is satisfying this condition that ARR of mid is less than the key. So finally what will happen is you will get start will become the actual index. Okay, it was earlier 13577. So then it was at index, I think, just a minute. Yeah, it was at index 4 initially. It will become 4 plus 1, counting from 0. All right. It will become 5, whereas end is still at 4. So what will happen? That loop which you see over here will terminate. All right. I'm trying to just explain the process of binary search. Later problems, you can yourself suitably modify the conditions, but it is important to get how you modify the conditions. Okay. So finally, so what is the original thing? It was 1, 3. This was the original thing. Sorry, I think this. Yeah, this was the original array. And yeah, it was, by the way, this 7. So its index was 4. Now start will become 4 plus 1 will become 5. End is at 4. So finally, if you see the index, the actual index I want will be given by start only. All right. It will be given by start minus 1. Because actually what you did was over here, if you see, start equals mid plus 1. And then the loop terminated. The loop terminated. So then to get back that value of mid, what you will do? You'll do start minus 1, which is basically 4. And yeah, it makes sense. This was originally our answer, right? We are searching we are searching for an element that is not greater than 8. It is 7. All right. So finally, we will, if they're asking starting from 1, the indices, then you have to print mid plus 1. All right. You have to print mid plus 1. Sorry. So you will get 4 plus 1, which will be 5, which will be the fifth element. All right. So now let me quickly come to two functions that are used. Just a minute. Yeah. You have lower bound and upper bound. And by the way, in CP problems, we generally use vectors. We extensively use vectors instead of arrays. So, and I think you are familiar with what is v dot begin and v dot end. Here v is your vector. So now, what is lower bound function? Lower bound function is used to find the next smallest number, which is just greater than equals that number. All right. And if there are multiple values, you'll return the first instance. So you'll return the smallest instance. All right. But upper bound returns the first instance of an element that is greater than the value that we have put on over here. Can you see this value? It will return the first instance. All right. How do we access that? We generally, I will just show an example. Consider this vector. All right. It has these elements. Now, if I want lower bound of 7, what is lower bound of 7? Sorry, not lower bound of 7. It should be lower bound of, it should be lower bound of 8 actually, my bad. Because lower bound of 7 is actually 7 itself. All right. We will do star of lower bound v dot begin, v dot end, comma 7. All right. This will give you the value of lower bound. If that element is present, it will just print the, it will just return the same value. In this case, it should have been, it'll just show 7 again. But if you want the index, all right, for index, what we need to do? We need to do lower bound of v dot begin, v dot end, comma 7, the value we want, minus v dot begin. All right. We can do similar things with upper bound also. All right. Upper bound of 7, not 7, 8 will 7 and even 8. In that case, it will give you the value 9. If we do star of upper bound, v dot begin, comma v dot end, comma 7, we will get 9. I will just, make a correction to this later. All right. Yeah. And there's one more useful function called binary search, binary underscore search. All right. This is actually a hyperlink. You can read more about it later. So basically, this function represents whether the element you're searching is present in the vector or not. All right. But the thing is, we generally don't want that. We generally modify the binary search condition and we do other things with it. So that's why don't get carried away by this. I've just included it for reference. All right. Yeah. A more general algorithm. I told you that we are generally dealing with arrays and which are generally sorted. All right. You have seen all our examples have been sorted arrays. We are splitting halves, comparing things and getting an element. But suppose we want something more general. We can actually do on a collection, on an array of numbers from 1 to n or 0 to n. And then instead of, checking whether it is located left side or right side, I will say that, is this satisfying the condition? Till what number is this satisfying this condition? And I will see the maximum possible value till it's satisfying. All right, let's go to a very popular example. If I just keep speaking about this theoretically, it doesn't make sense. Let us just see an example. This is a general layout, okay, of what I just said. Let's build a square root function for integers. Now, consider an integer, say 29. You will say that Arav, it doesn't have a square root. It is not a perfect square. Well, what I want is that I want the floor of that value, okay? The floor of that. And if you remember, I think in some group it was asked long back to build it in logarithmic time complexity. We are going to do this today. All right. If it is 29, I still want the answer 5. Now think about this. Why is the answer 5? You have to first of all think that how will you apply binary search here? I am telling you right now, binary search will be applied here. But if a general question comes, you have to come up with the logic. So if binary search is applicable here, there must be some comparison condition, right? So now, as I said, you can apply on numbers from 0 to n. All right. Instead of choosing an array and say ARR of mid, I will directly go with starting equals 0, ending equals n. All right. In this case, n is the given number. And then I will check if that middle value, mid, if the square of that value is less than equals the number I have been given, n. Alright. If that is less than equals that, then it is what you say a prospective answer. I'm using this word prospective answer because there are many possible answers, but only we want the maximum possible. Because if you see technically even 4 into 4 is less than 29, but we want the maximum among them. So we will keep searching till we find the maximum prospective answer in this case. All right. So the condition will be mid into mid is less than or equals n. Then now what I will do is I will store this answer in some variable. I will store this answer in some variable, say ans, ans. We generally use that. All right. Let me just show you here. As I said, we are applying on the collection of numbers from 0 to n. And I told you the comparison condition, whether mid into mid equals our number or not, less equals or is less or is greater. If it is equals means we have an exact answer. There is one unique answer and we will break over them. If it is less than that, then I told you, like in the case of 29, you have multiple possible prospective answers. I want the maximum among these prospective answers. So I will say start. I will basically shift. All right. As we had done in the first example, if it is less than that, then we are going to just shift. Start equals mid plus 1. We are trying to, why are we shifting in this case though? We are shifting to find better prospective answers. If mid is satisfying, who knows? Maybe mid plus 1 also satisfies. But we are even storing the previous answer in a variable. All right. Remember, we are storing our answer in a variable and then we are shifting. And suppose mid into mid is greater than number. Then is this a prospective answer? If I say 6, can I say 6 is a prospective answer in the case of 29? No, it is not. 6 into 6 is greater than 29. It is not what we need. That's for sure, confirmed. So we don't need to store the value in that case. And if you notice, rest of the code is same. We just added 2 lines here. All right. Yeah. So this is the general function to calculate the square root. So this method in which we didn't use a given array, we search for something from 0 to n and we use our own condition. In this case, whether mid into mid is greater than equals n. This thing is called binary search on answer. All right. Binary search on answer. All right. All right. This is an example. Actually, I think we'll be running short on time here. So I will just quickly go through this. Ideally, what I would have wanted was I would solve this over here. All right. So yeah, just a second. I've linked the problem here. I'll directly go to the problem. It is open here. Vasily likes to rest after a hard work. And I will not read the, unimportant stuff. He is interested in a drink called B Cola, which can be bought in n different shops in the city. And price of one bottle in the ith shop equals xi coins. All right. And he wants to buy his favorite drink for q consecutive days. And on the ith day, he'll be able to spend mi coins. All right. Now for each day, he wants to know in how many shops he can buy a bottle of B Cola. All right. This is an example test case. All right. Let me just open this to explain. Suppose you have here 3, 10, 8, 6, and 11. What is this? this price of one bottle in the ith shop, equaling these many coins. All right. And then suppose day one, he has only 4 coins. In how many shops he can buy? Only one shop. All right. Just a minute. My bad. 4 is actually, yes. One thing is there, whenever you do a problem, you should read the input lines properly. So, and I didn't do it in this case. It's 4 lines of input. First case was 1. If he has only 1 coin, can he buy in any of the shops? He cannot. All right. So what will be the answer? Answer will be 0 in this case. Now, similarly, if it is 10, he can buy in 4 shops and so on. All right. So now, logically speaking, you may ask, why do we need to apply binary search? Well, what would you do if you don't apply binary search? You would basically check for every element. What will you do? You will run a for loop or something for I equals 1 to 5. And then you'll check if that, suppose on a general day, suppose this is sick, they have given this as some, he has some money. If the cost of that bottle is greater than that money, then he cannot buy. Else, he can buy. He can buy that and increase the count of what he can buy by 1. All right. That's what he would do. But the thing is that this is a linear search and you will exceed the time limit for larger values. I have tried that. You please do not try that. All right. So that's why, if you notice here, the order of the elements does not matter. So we can just do sort. All right. We will just sort this entire thing. All right. And now you see. Yeah. Now we just need to locate. Can he buy anything with 1 coin? No, he cannot buy anything with 1 coin. Similarly, 10 coins, he can buy 4 things. So I am just seeing how many bottles, how many shops he can go and buy a bottle using the given number of coins on a particular day. All right. If you think about it, it is similar to our closest to the left problem. Only thing is, in this case, the index what we are getting, right? That will directly give you the number of coins, number of shops he can go to. All right. You have to just check the maximum index in which cost of a bottle is less than equals number of coins he can spend. All right. You can just check this. So either you do a binary search and do the method I was trying to tell, or I'll give you a 1-line hint. So you know the upper bound, right? The upper bound will just give you the element that is just greater than what we need. So if he has some money, as I said money, first of all, how do we write this? We write v dot begin, v dot end, and the money. All right, upper bound of that minus v dot begin will give you the index. All right, this will give you the index, but I'll give you starting from 0. And if you see, suppose let's take 3. Upper bound of 3 is 6. All right, and observe that this value is basically 1 and it matches with what we want. All right. Now let us plug in, say 10. What is element just greater than 10? It is 11. Then what we are supposed to do is we are supposed to, all right, that will give you index of this element. And actually, since this is numbered from 0, we'll again add a 1. So it actually doesn't matter. It is just this. You run a for loop. You first of all sort this. Then you run a for loop and check this. All right, where money is each of these values. All right. Upper and lower bound are very useful functions if you see. You can still try out the binary search way though. All right. Summing up, we have discussed the essence of what is a search. We have discussed how much faster is a binary search than a linear search using that example initially we had. Then after that, we discussed a general binary search and then a modified method binary search and answer along with some examples. And if you have noticed, I have stressed about how we are splitting the elements, how we are splitting the array and choosing the part that we want. If you get this logic, coding it is just copy paste, which due to time constraints, I haven't been able to do. But you can very well try that out. Having understood this logic, how you're supposed to split elements. And then I discussed two useful functions, lower bound and upper bound. And I'd even discussed about binary search function, which in my opinion you could avoid. But if the question asks you to find if an element is there or not, you could directly use that. All right. Are there any alternatives? Well, in this case, we divided an array into two parts and observed how much faster it is. How about I divide it into three parts and keep doing this? This thing is actually called a ternary search. You can look up more about it, but yeah, it is too complicated to discuss here. All right then. Thank you so much. It was a pleasure taking this. I'm really sorry for the in-between internet issues. But yes, let's move on.
Hello everyone, I am Aditya Jain, one of the coordinator of Programming Club IITM, and I'll be taking the second part of this session today. I'll be teaching you two pointers, and trust me, two pointers is a very, very useful technique, especially when it comes to competitive programming. So first of all, I would like to make a few things clear about two pointers. First of all, two pointers has no relation with pointers that many of you have studied in Codecraft session. Second, two pointers is more about implementation. It's more about practice. So basically, I'll be dividing this session into three questions. In each of those three questions, I'll be explaining you how to implement two pointers technique. So without wasting much time, let's begin with the first question. So basically, the first question is, you have an array of 9 integers. You have a sorted
Excuse me,
array of
Aditya.
9. Yes, Aro?
Are you presenting your screen?
Oh, it's not visible.
To me, it is
Great.
not visible. Let me just check once.
I hope it should be visible. Someone please confirm.
All right, it's visible now.
Okay, fine. Okay. So let's begin with the first question. In this question, you have a sorted array of 9 integers. Sorted array means the upcoming element will be either greater than or equal to the element that is just before it. So you have a sorted array of 9 integers. You have to find two such indices, I comma j, such that the sum of ai plus aj is equal to 11. That is, you have to find two numbers in this array such that their sum is equal to 11. Basically, you can do this problem without two pointers also. Like, I would like you guys to think over this problem for a minute or two. You can do it in time complexity of n log n. Log n is a hint. Try to think about any approach that you know for this question and write it in the chat box or put it in Slido. I'll be waiting for 1 or 2 minutes for you guys to think. Okay, fine. So first, let me share with you all the binary search approach for this problem. You can do this problem using binary search and time complexity of n log n. So So let's discuss the binary search approach for this problem. Basically, for every element of this array, you will check whether 11 minus that element is present in the remaining array or not. For example, for the first element 1 of this array, you will check whether 10 is available in this array or not. If 10 is available, then you have two numbers 1 and 10 such that their sum is equal to 11. For 3, you will check whether 8 is available in this array or not. So basically, you'll be implementing a binary search algorithm for each of these n elements of this array. For example, for 1, you will check whether 10 is available in this array or not using binary search. Since a binary search is log n approach operations, and you're implementing a binary search algorithm for each of these n elements of this array, therefore, the time complexity of solving this question would be n log n. However, using two pointers, you can do it in linear time complexity. So before sharing the two-pointer approach of this problem, I would like to give you a very vague idea of what is two pointers. So what is two pointers? Two pointers is basically you have two variables. They point to two different things. You change those variables depending on certain parameters. What are those variables? What do they point to? What are those parameters? You all will learn through practice. You all will learn through question. So let me share the two-pointer approach of the first question. So as I told you, we have two variables. So we have two variables, I and j. They point to two different things. So I is pointing to the first element of this array and j is pointing to the last element of this array. So that means I is equal to 0 and j is equal to 8. J is 8 because we have an array of 9 integers. So the index of the last element is 9 minus 1, that is 8. Now, what our goal is to find two numbers whose sum is equal to 11. That is, our goal is to find I comma j such that ai plus aj is equal to 11. Now, if you clearly see, now ai is 1 and aj is 11. That is, sum of ai plus aj is equal to 12. However, we wanted the sum to be equal to 11. So, we need to decrease the sum of ai plus aj now. Now we have two options. Either we can increase I or we can decrease j. So if you clearly see, if we increase I, the sum will be even greater than 12 because this is a sorted array and every upcoming element is greater than the previous element. So what we will do is we will decrease j. Thus, if ai plus aj is greater than 11, what we are doing, we are decreasing j by 1. Also, I would like you guys to understand the codes that I have written in these white boxes very nicely because I'm just going to write all these white boxes together to build a final code for this problem. So in the first step, we initialize our two variables I and j. I is equal to 0 as it is pointing to the first element of this array and j is equal to 9 minus 1 that is 8 as it is pointing to the last element of the array. Now, if ai plus aj is greater than 11, this means we want to decrease the sum. So what we will do, we will decrease j by 1. However, also, it's also possible that ai plus aj is less than 11. What we are going to do in that case? First of all, we decrease j by 1 because here ai plus aj was 12. So we decrease j by 1. So now j will become 7. So now, since we decreased j in the last slide, thus I is still pointing to the first element of this array, but j is pointing to the second last element of this array. Now, what we want sum of ai plus aj to be equal to 11. Now, if you check the sum of ai plus aj now, ai is 1, aj is 8. Thus, the sum of ai plus aj is equal to 9, which is less than 11. This means we want to increase the sum now because we wanted the sum of ai plus aj to be equal to 11. And now it's 9, so we need to increase it. So you have, again, two options. Either you can increase I or you can increase j. However, if you increase j, then it will be a repetition of the case that we have covered just before. I was pointing to the first element, j was pointing to the last element. So it will be a repetition of the case that we have already covered before. So there is no use of incrementing j. We will increment I. So whenever ai plus aj is less than 11, that is, if ai plus aj is less than 11, we want to increase the sum. So we'll increment I by 1. Now, in our last case, ai plus aj was less than 11. So we incremented I. So now I points to the second element of this array and j points to the second last element of this array. Now, if you clearly check, ai is equal to 3, aj is equal to 8, ai plus aj is equal to 11. So yeah, we found a good pair. We found two numbers whose sum is equal to 11. Also, if you observe, its time complexity is on because we are just changing variables I and j once only in this process. So if ai plus aj is equal to 11, we are going to stop our process because we wanted one good pair and we already found it. So we'll stop. One more important thing is like, what if no such two numbers exist in this array such that their sum is equal to 11? What are you going to do in that case? You have to stop this process at some point of time. You can't do it for infinite time. So when to stop? Basically, when to stop, this thing becomes your condition inside the while loop in a two-pointer problem. So what is the condition inside while? Basically, whenever you want to stop the process, that thing becomes the condition inside the while loop. Now, if you clearly observe, if ai plus aj is greater than 11, we decrease j. If ai plus aj is less than 11, we increase I. Thus, in every iteration, we are either incrementing I or decrementing j by 1. Thus, if no such pair exists, a time will come when I and j both start pointing to the same element. We don't want this because we want two different numbers whose sum is equal to 11. Also, now, if you increment I or if you decrement j, it will be just a repetition of the cases that we have already covered before, which we don't want. So, well, like it would be like you have swapped I and j, but it doesn't really matter. So when we have to stop when I becomes equal to j. Thus, till when we have to do this process? We will do this process until I is not equal to j. As soon as I becomes equal to j, we'll break this process, we'll stop this process. So the condition inside the while loop becomes I not equal to j. That means as soon as I becomes equal to j, this while loop stops. So this is the condition of when to stop. Now, as I told you before, I'll be writing just these white boxes together to get the final code for this problem. So here is the code. These were the white boxes that I wrote before, and this is the actual code. I have just made very small modifications to these boxes to get the final code. So let me explain you the code now. In this code, like I have given a generalized case. We have an array of size n, and was 9 in our case. In the question which I showed you before, n was 9 in our case. But this is a generalized case. We have n equal to 9. This I am taking an array of n integers as the input. This is int x. X is basically the number of which you find, like x is first 11 in our case. We want to find two numbers in this array whose sum is equal to x. Okay. Now, as I told you, I was pointing to the first element of this array and J was pointing to the last element of this array. Thus, I is equal to 0 and J is equal to n minus 1. We have an array of size n. So the index of J is the index of the last element, that is n minus 1. This is the same condition that I have written here, but for a generalized case. Now, this while condition I have written again here while I not equal to J. If ai plus aj is greater than 11, that means we want to decrease the sum. So we are decreasing j. I have written the same condition here. If ai plus aj is greater than x, x is 11 in our case. So if ai plus aj is greater than x, I am decreasing j. Now, the second condition was if ai plus aj is less than 11, what we are doing, we are incrementing I. So else if ai plus aj is less than x, that means ai plus aj is less than 11 in our case. So we have to increase the sum. So I'll increment I by 1. Else if ai plus aj is equal to 11, that means what? We have found a pair of numbers whose sum is equal to x. So if ai plus aj is equal to x, we stop. Stop. So like stop, no such word stop exists in C++. We use the word break instead. So whenever you use break, your loop breaks. So whenever you find you find two numbers, ai plus aj, whose sum is equal to x, you will break the loop, you will stop the process. So this is all the code. This is the code for the first problem. If you clearly observe, like I have made very small modifications. Instead of three if statements, I have clubbed them using else if. This is because if you clearly see, either ai plus aj will be greater than 11, or it will be less than 11, or it will be equal to 11. Thus, at one time, only one of these three statements is going to get executed. So it's better to club these statements using if and else if to make your good appear better. That's it. So this is the code for the first problem. Now, let's move on to the second problem. Okay. So this is the second problem, merge the arrays. What is this question? Basically, you have two arrays, two sorted arrays, array A and array B. Again, two sorted arrays. What you want to do is you want to put all the elements of array A and array B into another array or vector C, and all the elements in vector C should be in ascending order, should be sorted. For example, if your array A is this and your array B is this, what is the expected C? Expected C is basically you will put all the elements of array A and array B in another array C such that all the elements in array C are sorted. For example, if array is this, array B is this, our array C or vector C is going to be this. So how you can do this problem? Actually, you all can do this problem without two pointers also. So think of some other way to do this problem. You can again do this problem in time complexity of n log n using the things that we have already taught you all guys in sessions. So I would like you guys to think over this problem for a minute or two. Then I'll share both the approaches, one 2.1 and one another approach for this question. So think of it, how you can do this in n log n time complexity. I'll wait for a minute or two. So let's begin with the session again. I'll share both the approaches for this problem. So first approach is we can do this problem using sort function. What we are going to do is we'll put all the elements of array A and array B in another array C in any random order. In this case, I have first put the elements of array A, 1, 4, 5, and then I have put the elements of array B in this array C. Then what I'll do, Like you can also do it other way. You can put first the elements of array B and array, then array A. It doesn't matter. Then what I'll do, I'll use the sort function, which the syntax of which is sort C comma C plus N, where N is the number of elements in array C, and I'll get the final sorted array. However, like this approach is very easy than the two-pointer approach, but since sort function has time complexity of n log n, therefore the time complexity of solving this problem using sort function becomes n log n. Again, we can do this problem using two pointers technique in linear time complex. Yes, we have an ON solution for this. So let me discuss the two pointer approach of this problem. So before discussing the two pointer approach, like I would like you guys to think something. Suppose you are manually putting elements of array A and array B into a vector C. So which element is going to be your first element? Which two numbers are you going to compare while putting the elements into array C? Just think of it and try to think now what your two variables I and J will be pointing to. I'll wait for you guys to think what your two variables I and J will be pointing to. If you find it out, write it in the chat box or put it on Slido. Actually, it's very important to identify what your two variables I and J will be pointing to. So if you identify it, write it in the chat box or put it on Slido. I'll be waiting for 2 minutes. So we have some responses from some of our participants. Yeah, like they are correct. I will be pointing to the first element of array A and J will be pointing to the first element of array B. This is because all the elements of array A are sorted, so we don't have to compare any two elements of array A. Similarly, all the elements of array B are also sorted, so we don't have to compare any two elements of array B also. So what we have to compare? We have to compare elements of array A with the elements of array B. So if you clearly observe, like if you are putting elements into the vector C manually, what you are going to do is you'll check which one is smaller, whether one is smaller or two is smaller. Suppose like, so one is smaller, so we'll put one into the vector C. Then you will check, like one you have already put into the vector C. Now you'll check whether two is smaller or four is smaller. Which one is smaller? You will put it again into the vector C. So this is the main idea behind the two pointers approach for this problem. So initially, I is equal to 0, j is equal to 0, as I is pointing to the first element of array A, and j is pointing to the first element of array B. Now, ai is less than bj. If you clearly see, 1 is less than 2. So what we are going to do is, we are going to insert the smaller element. That is, we'll insert the smaller element ai into the vector C. So now our vector C will now become this, and will increment the value of I by 1. So try to understand the code in this white box again. I'll again write all these white boxes together to build the code for the second problem. So if AI is less than BJ, what we are doing, we are pushing the smaller element into the vector C and incrementing I by 1. Now you must be wondering why I have these two more conditions. Actually, I have added two more conditions apart from AI less than BJ. That is I less than 3 and J less than 5. Why these conditions are there? Basically, what if I becomes equal to 3? I becomes equal to 3. That means like our array A has only 3 elements. Now, that the maximum index of it can be 3 minus 1, that is 2. Now, if I becomes equal to 3, then A of 3 doesn't make a significance. It is incorrect statement. Similarly, our array B has only 5 elements. So if J becomes equal to 5, then B of 5 doesn't make a significance because the maximum index of any element in array B can only be 5 minus 1, that is 4. So make sure you always add these conditions because like many students, many people face a lot of difficulties in two pointers. Actually, it shows them runtime error whenever they forget such conditions. So make sure whenever you are writing a two pointer problem code, you make sure like you take care of all such conditions that your maximum index, like your I or J, should always be less than the size of the array. So I hope you understood this code in this white box. Now, since 1 was less than 2, so we inserted 1 into the vector C and we moved I ahead by 1. Now, I is equal to 1 and j is equal to 0. I is pointing to the second element of array A and j is pointing to the first element of array B. Now, if you see 2 is less than 4, that is bj is less than ai. So what do you think? Now we should push 2 into the vector C or 4 into the vector C. Clearly, since we want C to be in sorted form, so we'll push the smaller element into the vector C. Thus, C dot push back bj. Bj is smaller, so we are inserting the smaller element into the vector C. After inserting bj, the vector C becomes this, and we incremented j by 1. So again, if j is less than 5 and n I is less than 3 and n bj is less than equal to ai, that means we'll insert the smaller element into the vector C and we'll increment j by 1. Why are we incrementing j by 1? We are incrementing j by 1 because if you have already put the first element of the array B into the vector C, now we'll compare the next element of the array B to the ith element of array A. So we are incrementing j by 1. Now, since we incremented j by 1, so I is again pointing to the second element of array A, but now j is also pointing to the second element of this array A. Again, ai is less than bj, 4 is less than 6, so ai is less than bj. We'll insert the smaller element into the vector C and we'll increment I by 1. Thus, now our vector C becomes 1. First we inserted 1, then we inserted 2, then we inserted 4. So our vector C becomes this. Now, again, we incremented I by 1. So now I is pointing to the third element of array A and j is pointing to the second element of array B. We will again compare ai and bj. Again, 5 is less than 6. So we'll insert the smaller element ai into the vector C. So now our vector C becomes 1, 2, 4, and 5. And we incremented I by 1. That is I is equal to I plus 1. Now, if you clearly observe, I was 2 here. Now we incremented I by 1. So what I becomes? I becomes equal to 3. That is, what does this logically mean that I is equal to 3? I is equal to 3, it means like we have already put all the elements of array A into the vector C. So like now no element is left in array A, so we have to put elements of array B only into the vector C. Thus, I is equal to 3, so no more elements are left in array A. So we'll push back, we'll insert the elements of array B into the vector C and we'll increment j by 1. That is, if I is equal to 3, that means there are no more elements left in array. So what we are going to do is, since no more elements are left in array, we have to put all the elements of array B one by one into the vector C. Thus, if I is equal to 3, what we'll do, we'll insert the element of array B into the vector C and we'll move j by one step forward. Now, again, when to stop. This is a very important condition. And when to stop thing becomes the condition inside while, as I have told you before. So, like logically, when you will stop doing this process? Basically, when you put all the elements of array A into the vector C and you put all the elements of array B into the vector C, at that point, you will stop. At that point, you are going to stop because like it's logic. Like there are no more elements left in array A and array B, so you have to stop. Thus, like when you will find out like what is the condition that will tell you that whether all the elements of array A and array B have already been put in vector C or not. For example, like okay, array A has 3 elements. Thus, if I becomes equal to 3, this means that I already put all the elements of array A into the vector C. Also, D has 5 elements. So if J becomes equal to 5, that means that we have already put all the elements of array B into the vector C. So when you have to stop, you will stop when I becomes equal to 3 and J becomes equal to 5. Because this means that you have already put all the elements of array A into the vector C, as well as you have already put all the elements of array B into the vector C. So what will be your condition inside the while loop? Till when you will run the loop? You will run the loop when I is less than 3 or j is less than 5. This means like if I is less than 3, it means that there are some elements left in array A. If j is less than 5, it means that there are some elements left in array B. So until there are elements left in any one of the array, we will run this process, we'll continue this process. Once I becomes equal to 3 and j becomes equal to 5, we will stop this process. So this is the condition inside the while loop. Now again, I'll be writing all the white blocks together to build the code for the second problem. Okay. So these are the white boxes that I showed you before, and this is the code. So this is a general case. Again, the question which I showed you in that array A has size 3. In our question, array A has size n. And in the question I showed you, array B has size 5. In this case, array B has size m. Basically, it's a generalized case. Now, let's look at the first statement. If I is less than 3 and then j is less than 5 and then bj is less than ai, that is I is less than n, j is less than 5, so j is less than m, and then bj is less than ai, that means we are inserting the smaller element bj into the vector C and are moving the pointer j by 1 forward. Now, else if. Again, I've clubbed these two statements using if and else if to make the code look better. Because if you clearly observe, this statement will get executed when I is less than n. This statement will get executed when I is equal to n. So I've clubbed these statements using if and else if. So else if I is equal to 3, else if I is equal to n. That means you don't have any element left in array A. All the elements of array A have already been put into vector C. So now you have to put all the elements of array B one by one into the vector C. So that's what I'm doing. I'm inserting bj into the vector C and moving j again by one step forward. Now else. This is slightly a new thing. Actually, I need to make some modifications to make it a correct code. So let's ask yourself a question. Actually, when you are inserting an element from array B to array to vector C, basically, whenever bj is less than ai, then you will insert element from array B into vector C. Otherwise, if there are no more elements left into the array, then you will insert elements from array B into the arrays into the vector C. So otherwise else, since if you're not putting an element from array B, you have to put an element from array A. So this thing like else statement takes care of that thing. So C dot pushback AI. That means if we aren't inserting element from array B, if we aren't inserting element from array B, then what we'll do, we'll insert element from array A into the vector C and we'll move I by one step forward. So this is all, this is the code for the second problem. I hope you understood this code. So you guys can scan the QR code and mark your attendance if you haven't done it yet. I'll wait for 2 minutes. Okay, I hope you all must have marked the attendance till now. If you haven't marked it yet, we'll share the link again at the end so you can mark it at that time. Let's begin with the third question. This is a bit tricky and like it's quite difficult. So what is this question? Basically, you have an array consisting of non-negative integers. Non-negative means all the elements will be either positive or will be equal to 0. You have an array consisting of non-negative integers. What you have to do is you have to find in this array the length of the longest segment such that the sum of all the elements of that segment does not exceed s. S is basically given to you through the input. So, and one more condition is there. All the elements of array A are less than or equal to S. So first of all, let me explain you what is a segment. Suppose you take two indices I and j. Thus, segment will be basically the sub-array consisting of all those elements of the array A with index from index I to index j. For example, we have an array A this. If you choose I equal to 1, that is I equal to 1 and j equal to 3, then the segment will be the sub-array consisting of all the elements from second to fourth element, consisting of second to fourth elements. Now, suppose you take element, you take the third element, then you take the fourth element. This is not a segment because first, third, and fourth element aren't consecutive. So a segment is basically any number of consecutive elements of an array. So I hope like now you know what is segment. So what you have to do is you have to find the longest segment in this array, the sum of whose elements should not exceed s. That is, the sum of all the elements of that particular segment should be less than or equal to s. So, like how you can do this using two pointers. Again, you will need two variables, I and j. What your two variables will be. So, I would like you guys to think what your two variables will be. If you like, it's difficult to identify in this case, but then write it in the chat box or put it on slider. I'll wait till 6:33. Okay, so let's begin with the solution for the third and last problem. What we are going to do is for every element of this array, we'll find the length of the longest segment that is starting from that element and is having sum less than equal to s. For example, like I'll repeat the statement again. For every element of this array, you'll find the longest segment that is starting from that specific element and has sum less than equal to s. For example, let's consider an example. X is equal to 5 and we have this array A. Now, for the first element, you will find the longest segment that is starting from the first element and has sum less than equal to s. Clearly, if you see the longest segment is the segment consisting of first four elements. Like first two elements also have sum equal to 2. First three elements have sum equal to 3, which is less than 5. First four elements have sum equal to 4, which is also less than 5. But if you consider the first 5 elements, it has sum equal to 6, which is greater than 5. So the longest segment, which is starting from the first element of this array A and has sum less than or equal to s, is basically the segment consisting of first 4 elements. Now, what I'll do is I'll repeat this process for each of these n elements of the array. For example, I'll repeat this process for the second element also. I'll find the longest segment, which is starting from the second element, and the sum of whose elements is less than equal to 5. For example, if I consider the segment starting from the second element of this array and going till the fifth element of this array, if you clearly see, this segment has sum 1 plus 1 plus 1 plus 2, that is 5. So this is another segment. This is starting from the second element of this array, and it's actually the longest segment that is starting from the second element of this array and is having sum less than equal to 5. If we include the sixth element, then its sum will become equal to 6. Thus, the longest segment, which starts from the second element of this array and is having sum of all its elements less than equal to 5, is 4. We'll repeat this process for each of the n elements of this array, and then we'll choose the maximum length among all such segments. Because in the question, we want the length of the longest segment. So I hope I have cleared my goal. My goal is for every element of this array, we'll find the longest segment starting from that element and having sum at most s. Okay. So we have our two variables I and j. In this case, initially, I and j points to the first element of this array A. Basically, if you realize, like I and j will point to the start and end of the segment respectively. Okay, so let's find the length of the longest segment, which is starting from the first element of this array. Okay, so initially I and j will be are both pointing to the first element of this array. We will add, what we'll do is we'll keep increasing j till sum becomes greater than s. For example, like I and j are both pointing to it. So what we'll do is we'll add the first element to the segment. Its sum is now equal to 1. Then we'll add the second element to this segment. Its sum is now 2. It's still less than s. Now we add the third element to this segment. It's still 3, which is less than 5. Now we'll add the fourth element to the segment. The sum is still 4. It's less than 5. Now what we'll do is whether we'll add this fifth element to this segment or not. Clearly think if we add the fifth element to this segment, then what will happen is our sum will become equal to 6. Thus, we don't want that and we'll stop the process. So what will happen is I is still pointing to the first element of this array and j is pointing to the fifth element of this array. This is because we have only included the first 4 elements in the segment. We haven't included the fifth element in this segment, because if we include the fifth element, then our sum of the segment will become greater than 5. It will become equal to 6, which we don't want. So we'll just include the first 4 elements of this array A into the segment S. Now, look at the code in this white block again. Yeah, look at the code in this white block again. While sum plus age is less than equal to s. What is this condition? This condition is basically, we will check, like after adding aj to the segment, whether the sum will be less than equal to s or greater than equal to s. If sum becomes greater than equal to s, then we won't add aj to the segment. This is because we want sum of that segment to be less than equal to s. Thus, we'll check this condition. If sum plus age is less than equal to s, what we'll do is we'll add aj to the sum and we'll move j by 1 step forward. We'll increment j by 1. So again, I have one extra condition here while j less than n. This is because, like, again, our array A has n elements. Now, if j becomes greater than or equal to n, then A of n doesn't make any sense because array A has n elements. So the maximum index can be n minus 1. So that becomes like wrong condition and it shows runtime error. So always make sure you include such conditions. So I'll explain this condition again. While j is less than n, that means there are array elements left in the array A, and sum plus aj is less than equal to s. This is the condition that we are writing because we will add aj, that is a particular element of the array A, to the segment if and only if, even after adding the element to the segment, the sum of the segment remains less than or equal to s. Thus, until the sum plus aj remains less than equal to s, we will add sum is equal to sum plus aj and j is equal to j plus 1. So let's run this loop on this example. Initially, our j is 0 and sum is 0. We have initialized sum to 0 initially. So j is 0. Now sum plus a0, that is equal to 1. Sum plus a0 is equal to 1. It is less than equal to 5. So we'll add first element of this array to the sum. So now sum becomes equal to 0 plus 1, that is 1. And j becomes j plus 1. J is equal to j plus 1. So j becomes 1 now. Now we again run this loop. J is 1, which is less than n. Now also sum plus a1. Our sum was 1 now. So sum plus a1, that is sum plus 1 is again less than equal to s. Sum plus 1 is 2 now. So it's again less than equal to 5. So we'll run this loop again. We'll keep on running this loop until any one of these conditions like become false. So if you clearly observe, we'll increment j till here. But now since the sum was 4 here now, and sum plus aj now becomes equal to 5, equal to 6, which is greater than 5, thus we'll break this loop and our sum becomes equal to 4. And our j points to the fifth element now. Thus our j points to this element and I still points to the first element of this array. Now, I points to the first element of this array, j points to the fifth element of this array. This is because we haven't included the jth element into our segment, because otherwise the sum of this segment will become equal to 6, which is greater than 5, and we don't want it. No, now, what is the length of the longest segment, which is starting from the first element of this array A and having sum at most 5? This is actually, if you see, it's equal to j minus I. J is 4 as it's pointing to the fifth element, and I is equal to 0 as it is pointing to the first element. Thus, the length of the longest segment, which is starting from the first element of this array A and is having sum less than equal to S, is equal to j minus I, that is 4 minus 0 equal to 4. Now, like we have done this process for just the first element of this array. Now, we have to do this process for each of these n elements. Now, we need to find such a segment for all the segments of this array. Let's calculate it for the second element. What do you mean by second element? It means like I will be pointing to 1. I'll be pointing to the second element of this array now. So I will be equal to 1. Now, I have a question. What sum includes till now? Sum is basically includes the first 4 elements of this array. Therefore, sum is equal to 4. Now, we want to find a segment which starts from the second element of this array. Thus, we'll subtract the first element from the sum. So sum is equal to sum minus ai. I was 0 before. So sum is equal to sum minus a0. Sum becomes 4 minus 1 equal to 3. Why I've done this basically? It's because we wanted to find, like we have already found the length of the longest segment which starts from the first element of this array and is having sum less than equal to s. Now I wanted to do it for the second element. So the thing is, the sum that we have calculated till now included the first 4 elements. But since now I want to calculate the segment which is starting from the second element, therefore I have to remove this first element from the sum. So I have removed this first element from the sum. Now, if you clearly observe, I points to the second element of this array now, and sum is equal to 3 now. Now, if you observe one thing, when I calculated the length of the longest segment initially, both I and j were pointing to the first element of this array. But now, I is pointing to the second element of array A, and j is pointing to the fifth element of this array A. So, should I make j equal to 1 again, or I can start running the loop from here on? If you clearly observe, now sum includes the sum includes basically all the elements from second to fourth, and it is less than 3. The sum of first 4 elements was less than equal to s. So the sum of elements from second to fourth is definitely going to be less than equal to s. Now, this, if you think like this is the segment which is starting from the second element of this array A and has sum less than equal to s. But it is not the longest segment starting from the second element of this array. So we might have to add the next element also into this segment. So we can start running the loop, while loop of j, like from here only. We don't have to make j again equal to 1. So let's see the code of this question. So this is the code for this question. It's slightly trickier. It's slightly difficult. So first of all, let's begin with this question. Like we have an array of size n and s. We have taken n and s as input. Now, here I have taken the array A as input. It's given that array A has non-negative integers. Now, I have a variable int max length is equal to 0. Basically, this variable will store the maximum length of a segment which has sum less than equal to s. Also, I have initialized sum equal to 0 and we have a pointer j equal to 0, as j was pointing to the first element of this array. Now, what we wanted is, we wanted to calculate for every element of this A, the segment which is starting from that element and is having sum less than equal to s. Thus, since we want to do this for each of the n elements of this array, we have a for loop here which is running from 0 to n. So I is going from 0 to n. Now, what is this condition? This is the same condition. This is the same statement that I had showed you in the white block before. So if while j less than n and sum plus aj is less than equal to s, I'll keep on adding aj to sum and will increment j by 1. So what I'm doing is I'll keep on I'll check like even after adding aj to the segment, if sum plus aj remains less than equal to s, I will add aj to the segment and I'll add some I'll add aj to the sum and will move the pointer j by one step forward. Now, what is this condition? Basically, when this loop breaks when like sum plus aj becomes greater than s. So in the example which I showed you before, it broke when j was 4 and I was 0. Now, what is j minus I? J minus I is basically the length of the segment, which is starting from the ith index. So like for the first element of this array, I is equal to 0. And in the example which I showed you before, j was 4. So we'll check if j minus I, that is the length of the new segment that we found just now, if it's greater than the maximum length of all the segments that have been found before, then what we'll do, we'll change the maximum length to j minus I. So that maximum length always stores the maximum length of such a segment. Now, what is this statement? Basically, we calculated the length of the longest segment, which starts from the first element. I was 0, suppose. So we calculated the length of the longest segment, which started from the first element of this array and had some less than equal to s. Now we want to repeat this process for the first element also. Now, if you clearly observe, like our sum included the first element. Now we want that our sum should not include the first element. Our sum should include the elements starting from the second element. Thus, we'll remove the first element from the sum and we'll repeat this entire process again. So this is the code for the third problem. I hope you understood it. Try to read it once again and you will understand it. So this is all about today's session. Scan this QR code and rate the session. Thank you. Also, there is a attendance link in that poll. So make sure to mark the attendance if you haven't done it yet. Yes, I would like you guys to scan this QR code. I have launched the poll. And you guys, thank you for your feedback. That's all about the today's meet. I hope you understood all the concepts well. So I'll end the meet for now. Thank you, everyone.